So last time, I guess let's get started. So last time we were talking about detonation shock dynamics, and which was basically discusses or basically is a theory that accounts for the fact that detonations, say in a high explosive charge, can be curved due to the high pressure pushing out a steel casing or something like that, and that produces expansion waves that gets into the reaction zone. And then those expansion waves basically lower the pressure in the reaction zone, and then which then affect the chemical reactions. And so there's this whole theory on detonation shock dynamics that was developed by Scott Stewart and Bsd that basically corrects for that. And so when we derive the equations, the structure equations using for curved detonation, they are essentially the same as they are for 1D planar. We are assuming weak curvature, except for there are these extra source terms to conservation of mass, conservation of momentum, and also the thermicity is also modified to account for the deceleration of the flow behind the due to the expansion wave. And now these detonations here, that is for a given detonation velocity, we don't know what the correct value of kappa is, or if you have a curved detonation, we're basically asking the question is how fast is the detonation going to propagate? If it's propagating in a quasi-steady capacity. And so we're given a value of kappa, and we want to find the equilibrium Chapman-Jagay detonate, or not Chapman-Jagay, just the detonation velocity. And the procedure here is a little bit more involved because we can't just go to the PV diagram and use the Rankine-Hugoniot relations. They don't tell us anything because they don't account for curved detonations. And so instead, we got basically there will be a sonic plane. And we require for equilibrium that the sonic plane and this modified thermicity go to 0 at the exact same point. And so if the sonic if the flow is sonic and the thermicity goes to 0 at the same point, we have ourselves a nice equilibrium detonation. And now this thermicity is also it's modified to account for this curvature effect on the streamlines behind the leading shock wave. Okay, and then also if kappa is 0, we do recover the standard 1D planar detonation structure equations. Okay, so I mentioned this before. And so, yeah, I figured, and now one thing to note, that because of this modified thermicity condition, that when the thermicity is 0, that does not necessarily mean that there are 0 chemical reactions. That means that sort of acceleration due to chemical reaction is being balanced by deceleration due to the sort of expanding streamlines behind the curved shock. And so for a general curvature, what this means is that the equilibrium equilibrium detonation for a curved detonation, there will still be some reaction occurring, meaning, and if there's still some reaction occurring, that means that at the sonic plane, we don't have the condition anymore that all of the reactants are consumed, is that the reactants are in a partially burned state. And so I basically showed that here, is that for a CJ detonation, all of the reactants are consumed at the sonic plane, and for curved detonation, they are not. And so there's a lot of leftover stuff that can burn, and it does in general burn, but it doesn't contribute to the detonation. It probably contributes more to the sort of the fireball or the afterburning process. Okay, now then we went over the procedure, how to find this, and that's what project 1 for you guys is all about. And now, in general, what you'll find is that if you plot the detonation velocity of the curved detonation as a function of the curvature of the leading shock, what you'll find is you'll either produce this sort of P-shaped curve or this S-shaped curve. right there. And so, and really what we're interested in for the most part for detonations is just this very top portion. And so either the P curve or the S curve is more or less the same. And so, and similar D versus kappa type of results have also been shown experimentally for this top branch. Okay, and so I know that it seems natural to think of the detonation velocity as a function of kappa, but in general, there are 3 different parameters, and that is a much more difficult way to solve this problem. In general, it is, but you can see that for every detonation velocity, there is only one value of kappa. So when you are searching for the equilibrium detonation, the equilibrium combination of kappa and the detonation velocity, is that it is much easier to think of D being on the being on the x-axis and kappa being on the y-axis and making that curve, because then it's a function of just one variable. In the early works, they did it the hard way, and then finding this S-shaped curve was much more involved. But then I think a student of Scott's basically said, why don't we just flip it around and basically put D down here and kappa over here, and then it's just a function of one variable. And then it became much easier for them. Okay, and so what this means is that the higher the curvature of the detonation is, the slower it goes, until it reaches this critical point, and then the detonation essentially fails. Is that you just have a shock with some burning stuff behind it, but they are not fully coupled together to produce a self-propagating detonation anymore. Okay, and so now how this is actually used in a lot of codes is that you'll often fit some sort of linear relationship to just this top portion of the curve, because again, in most setups, your detonation, you will design it to be fairly weakly curved. You want to avoid very strongly curved detonations because you don't want the curvature to be so high that you produce localized regions where the explosive doesn't burn and contribute to the detonation. And I mean, there's a multitude of reasons for that, efficiency, things like that. And so what they'll do is they'll just fit some sort of really simple function, sometimes a linear fit, sometimes something else, and then they'll fit that. And so if it's a linear fit, they'll have DCJ, they'll have that the detonation velocity is equal to the Chapman-Jagay detonation velocity minus some coefficient times the curvature. Or if they're doing some sort of rate stick, and again, a rate stick is just like a stick of dynamite, and you have a detonation wave, oops, wrong one, a detonation wave propagating through it. And if it's above the critical radius that will support a detonation, that is the curvature of the detonation as it propagates through isn't so high that the detonation fails just due to the stick of dynamite being too small. What they'll do is they'll fit it a little bit differently. And so for these rate sticks, the curve fit will look something like this. Okay, and then here's just a table from Zukis and Walters that shows for various explosives what DCJ is, and this would be D infinity equals DCJ, and what the critical radius is and what A is. Okay, and then this is what RC is. RC is just a constant, and this is what the experimental critical failure radius is for a rate stick for a given explosive. Okay, and these are uncased, and by uncased I mean they just have a piece of paper around them or something like that to sort of protect them from getting dirty and hold the stuff together. But it isn't like a thick steel casing or like anything like that. Okay, so are there any questions on this? And so this detonation shock dynamics sort of motivates a lot of these functional forms, and it also nicely explains a lot of the features of what have been observed in these experiments. And then for other charges, they'll sometimes just do a nice straight up linear fit, like I showed before, where d will be dCj times the quantity 1 minus a constant over the diameter. And recall that kappa for some sort of stick will be, I'll just say, either 1 or 2 over the diameter, depending on whether it's a sphere or some sort of cylinder. Okay, and so basically this this 1 over d here, that is just representative of the curvature. Okay, and so, and then for that type of curve fit, you see basically additional data here. Okay, and so again, these are just curve fits to experimental data, and the experimental data shows the exact same sorts of trends that the detonation shock dynamics showed. Okay, now these were for essentially uncased explosives. Most explosives have some sort of casing for a confinement effect, such as we have a high explosive here. We have a steel casing. And the fact that there's casing there greatly changes how these expansion waves, oops, sorry, I'm bumping the thing with my wrist, greatly changes how these expansion waves form that propagate inside of the reaction zone from the side relief that is produced by the gas flowing out the side of the explosive charge, because essentially before the expansion waves can form, the high pressure needs to push the casing out of the way. Then after the casing gets pushed out of the way, then the gases can expand. But it takes time and distance for this casing to be pushed out of the way because it's really heavy. And it also has strength. And so the fact that the casing is there or not there changes how these expansion waves form that propagate inside of the reaction zone. And so the correlations for that for a steel cased rate stick are completely different. And so here is just a correlation from Cooper, and it just has a rate stick, but it's encased by but the sort of solid explosive is basically pressed inside of a steel sleeve. And then from data, they did a curve fit, and then they find that the detonation velocity here that propagates through the explosive is a function of A and D, which again are very similar curve fits from experimental data. In fact, they are the same A and they are the same A that is in this table right here. Okay, and then WHE is the weight of the explosive, and W steel is the weight of the steel. Again, this assumes that the explosive is a cylinder and the steel is a perfect annulus or a perfect tube that you're just sort of pressing the explosive in. So basically, all of the fact that the sort of thickness of the steel casing and the length and all that stuff is sort of baked into these weights. Okay, and so this is just nothing more than an experimental correlation. It's not based on theory that I know of, and so basically, but you notice that that the higher the weight of the steel, the better the confinement is, and the faster the detonation propagates. Okay, and again, for this expression to be valid, there must be, I don't know what the minimal thickness is of the steel casing for this expression to be valid. It clearly does not work for an uncased charge because it does not limit itself to the detonation velocity for an uncased charge. Okay, so just be careful of that. If you ever need these sorts of correlations in your work down the road, there are all kinds of them. Just you have to do your due diligence and look and check and make sure that you're using them for the exact sort of specific conditions that they are designed for. Because if you're using it in an incorrect regime, you can get completely wrong results. And sometimes you are in a regime where where there is not any correlation that exists. And so then you're just going to have to pick the sort of best of the worst models and just use your engineering judgment to sort of make your design decision from basically that point on, or you do a more advanced sort of reactive burn type model for it if it's really crucial for your application. Okay.
What is the value in front of the weight of the high explosive and weight of steel?
8.7.
Okay, so thank you.
Yep. I believe that does look like an 8.7. So,
Professor, for this, you say steel too, but does this only apply to steel? Like, have people done this with like aluminum? Is it a different relation if it was like aluminum or something?
Yes, it's a different relation. There's a different constant here, and even the power here might be different.
Okay.
Yeah, and even the wave structure might be different. One of the most interesting, and I don't think it's fit to a functional form like this, is if you have the explosive here, and the liner isn't steel. But the liner is beryllium. The reason that's interesting is that the speed of sound in beryllium is extremely high. It's faster than most detonation velocities. So what does that mean? If you have a detonation wave propagating through a high explosive, but the sound speed of the confiner is faster than the detonation wave speed, that means the pressure information from the detonation goes into the casing and actually propagates ahead of the detonation, and that actually reduces the curvature effect. And so there are really interesting gas dynamic or compressible flow effects. And so the wave structure for that does not look like this. It looks more like this. You'll see a tiny little bit of curvature. The shock will basically jump out in front. Then it'll be transmitted like that. And so the shock will actually be detached and run in front of the detonation. It's really weird how that happens, but it does. And so basically, all of this correlation here is taking into the consideration the details of how the shock of the detonation interacts and then propagates into the casing material. And that's very, very material dependent. Okay, but they used beryllium for experimental things. You couldn't use it for anything practical because if you burn, because beryllium, the combustion products of beryllium are toxic. I had a colleague who took class at Princeton for rockets, and when we get to the multi-phase aspect of this class and discuss particle combustion, both per unit or per unit mass and per unit volume, burning and from an ignition standpoint, Be particles or beryllium are the perfect material. They have a huge amount of energy. They burn and they burn up easily. Unfortunately, the reason that they're not used in rocket propellants as an additive is that their combustion products are toxic. Is that basically flying them over the enemy and the rocket plumes, and then the people breathing in the products from the rocket plume would almost qualify them as a chemical weapon. Is that they're that toxic, and so that's why BEs. That's why they're not used. Oh, go ahead.
I was just reacting to the toxicity of the rocket plumes. That's crazy. Yeah,
it's very. So that's why it's not used as like when and that plot I'm going to show in about 3 weeks is striking. But it's not used for that reason, is that it's just too toxic.
Okay.
Okay, and then and that means for those of you that actually work with propellants, when you open up the crates, you need to use anti-sparking tools, and that for obvious reasons. And anti-sparking tools are made of beryllium often. So you need to be very careful that you don't actually, produce any sparks or small chips of your tools when you do that. Yeah.
Usually we make them out of beryllium copper, and beryllium copper is not toxic to handle or any
Okay.
of that, or machine even. But I imagine if you combust beryllium copper, you're still gonna break it down into a toxic
Yep.
material.
Yeah, you do. Yeah, I imagine if there's a fire in your sort of shipment receiving facility where you open the stuff up, or your bunker, or wherever you do it. Yeah, I'm pretty sure if there's a fire in there, you probably don't want to be anywhere near those tools. Although beryllium copper might have a hard time burning. I don't know.
Yeah, it does. It's actually really nice to machine, and you can machine with it without it being toxic, and it doesn't really have any issues. But yeah,
cool. Okay, so now we determine these d kappa relations, and so how are they actually used? Either if you determine them empirically, or if you determine them from detonation shock dynamics. And they are useful for more than just determining the critical diameter. Is that you can actually use them to propagate the detonation surface without needing to perform a full-fledged reactive burn simulation. And now I will make a caveat here: is this is more useful for explosives because the structure of a multidimensional detonation in a solid is very nice and simple, whereas the detonation structure for a gas becomes very it's inherently unstable, and basically bumps start to form on them, but say solids don't do that. And so this theory is very successful for solids. It's almost never used for gases. Scott does extend DSD theory to include the acceleration of the shock front. And if you include that effect, you can actually use this for gases too. But that is a much more complicated version of the theory. And him and Bidzil are the only ones that I am aware of that do that. Okay. But so how this is used is let's just define a surface function psi. And so psi will be a function of the position vector and time. And we're going to define the surface of the detonation with psi being 0. Okay, and so if we have our psi here, this is our detonation. Psi is defined to be 0 on the surface of the detonation. Okay, and so we have our detonation surface here. And we know that the detonation, it propagates normal to itself. So if we have a normal vector pointing out here, it's going to propagate normal to itself at some velocity un, and it has a different normal. It has a different normal vector here, and at this location, it's going to propagate outward normal to itself into the reactants at some other propagation velocity. Okay, and so the detonation propagates normal to itself, and that normal propagation velocity is just the dn that we get from the d kappa theory or Dsd theory, and the direction is just the normal vector, and we are defining the normal vector because we have the choice of 2 directions as pointing towards the reactants. Okay, and so now we want to find an equation that we can use to describe the motion of the surface. And really what we do here is this is our surface equation here. We're free, and we're sort of free to define some properties of psi, and I will get into that a bit later on because there's a very common one that is used because it has very nice properties. But basically, to derive how the psi evolves, we just take we use the chain rule, and we take the total time derivative. And I'm not going to go through that derivation because it's identical to the derivation that you did either in FM1 or even undergrad fluids when you guys dealt with the substantial derivative, is that you wind up with the exact same thing. And so you wind up with the total time derivative, or the Lagrangian motion of the surface, is given by the time derivative of psi plus dx dt dotted with the gradient of psi. So again, this is a bit more lengthy of a derivation, but most undergrad classes in fluids do this. So I'm skipping about a page of work. Okay, and this dx dt is nothing more than the local velocity of the detonation surface. So are there any questions to this point? Okay, so now we want this dx dt to be the local velocity of the detonation surface. So we're going to define that to be the velocity vector of the surface in the normal direction, because again, we know that the detonation propagates normal to itself. Okay, and so that equals the dn times n hat. Okay, so we could basically take this and then substitute it in, but now we have our arbitrary curves, or we have our arbitrary surface. How on earth do we find n hat? Well, it turns out, then I'm not going to go through this. I've actually never seen this derivation, but it turns out that n hat can be computed by just taking the gradient of our surface function and dividing it by the magnitude of the surface function, or the magnitude of the gradient of the surface function, and then that gives you n hat. Okay, and that I think probably harkens back to Calc 1 or either Calc 1 or Calc 3. I can't remember which. Okay, so again, so just treat this as a definition if you are unfamiliar with it. If you work with propellants, multi-phase flows, you will be dealing with this sort of equation quite a bit. Okay, or even immersed boundary methods for gas dynamics. You'll be dealing with this quite a bit. Okay, and so now we know n hat in terms of psi, we know dn, and so we know that the dx dt then that we can substitute into our motion rule for the detonation surface is just dn, which comes from Dsd theory, or d kappa correlation, and then multiplied by n hat. Okay, oops. Then we take this, and I have a little typo here. Then dx dt dotted with grad psi is equal to dn times grad psi dot with grad psi over the magnitude of grad psi, but grad psi dotted with grad psi is just the magnitude of grad psi squared. And so we got a magnitude squared over the magnitude. And so this whole term here just becomes the local normal component of, or the local detonation velocity that accounts for curvature times the magnitude of the gradient of psi. Okay, and so we can substitute this in to here. And when we do that, we get an evolution equation for the detonation surface. Okay, and so that's just this equation here. And here I just explicitly wrote that the normal velocity is a function of the curvature, and the curvature is given by can be computed by just taking the divergence of the normal vector. Okay, and you can sort of see that if you have a circle-y surface here, the n hats point out. And you can see that basically the sort of rate at which they sort of point out you could compute using the divergence, and you can see that the smaller the circle is, the sort of more they point out. I'm explaining this poorly, but you can sort of almost picture it in your mind that the curvature of a surface is related to how two nearby normal is related to how two nearby normal vectors point away from each other. Okay, because if they're perfectly parallel, you have no curvature, and if they are if they are pointing significantly far apart, you have a large degree of curvature on the surface. Okay, and so this is the equation that we want to solve. But now we've only defined one property of psi thus far. I mean, these are just consequences of just pure mathematics. It doesn't matter what psi is. And the only property of psi that we've defined is that it is 0 on the detonation surface, and that's it. And so for some other properties to give it a nice sort of mathematical structure, one that we can actually solve, that we can go to the computer and solve this fairly easily, or I should say easily, is to define psi to be a sine distance function. And so what we do is we define psi to be greater than 0 in the unburned explosive. We define psi to be less than 0 in the products. And again, we are forced to define psi to be 0 on the detonation surface. Okay, and so say out here in the green where we have unburned explosive, we have this weird, goofy curve-shaped detonation that is propagating outward. Again, each point on the surface is propagating normal to itself. Okay, and so basically out here, psi is positive, and in here in the products, psi is negative. Then that means if we define the normal vector as the gradient of psi over the magnitude of that gradient, that means it will naturally point that the normal vector will naturally point into the reactance, which is what we want. Okay, but now there's one other property, is that now we know it's negative here and positive here, and 0 on the detonation surface. But now we're going to be taking gradients of this and curvatures and all sorts of things. So because we could define this function to be -1 here, +1 here, and 0 here everywhere, that works. But it would be really hard to solve that equation accurately. So what they then add is this extra constraint on psi, is that the magnitude of the gradient of psi is defined to be 1. And now you got to think about that one a bit, but what that does is that forces psi to be what's called a Euclidean distance. And so that's why this psi is called a sine distance function. And so essentially what this gradient being, what the magnitude of the gradient being 1 means is that you can think of psi as an elevation map. And the gradient, and basically no matter where we are standing, here or here or here or here or here, is that no matter where we are standing, the slope is always 45 degrees. Now that 45-degree slope might be pointing in different directions, but it is always 45 degrees. Okay, and you can think of on the elevation map, a sea level will be the detonation surface. In the explosive, that will be above sea level, and in the products, that will be below sea level. Okay, and so what the slope of 45 degree means, which is sort of which is basically what this states, but just in a different way, is that the magnitude of psi tells us exactly how far we are from the surface. So for example, if psi is 1 centimeter, that means that we are exactly 1 centimeter away from the nearest point of the detonation surface. And then the sign of psi tells us which region we are in. So if psi is plus 1 centimeters, that means we are 1 centimeter. That means that given point is 1 centimeter away from the surface in the explosive. If psi is minus 1 centimeter, that means we are 1 centimeter away from the nearest point of the surface, and we are in the product region. Okay, so does that make sense? Are there any questions here? You'll see the sine distance function being used in a whole lot of contexts because it is very nice. It's used in multi-phase flows. I know Tom Jackson's group uses it a lot for their stuff. I think his SDT code and his heterogeneous propellant combustion code they used all kinds of level sets to define all sorts of different surfaces. So these things are used a lot and for a lot of really practical applications. Okay. And so that just defines what psi is. And there's all sorts of literature that if you actually want to construct the sine distance function for a complex surface, there are multiple ways of doing that. And one of my grad students has done that. Basically, that we can read in CAD geometry into our code, and you can make a sine distance function of a really crazy convoluted CAD geometry shape. And so there are multiple ways of doing that. For your class project, I believe you're punching in a rectangle, and so you can define that with a nice exact function. But more complicated shapes, you need to do something much more involved. Okay, so now let's just examine the case that if the detonation velocity is equal to the CJ velocity, and we're just going to do a linear fit on the d kappa relationship. And so it'll be minus alpha times the curvature. Okay, and alpha is basically just some fit. Is basically just some slope parameter here. Okay, well, we know that, so we have our sine distance function and we wish to evolve it. And so we have our dn here, and now we're just going to substitute this in. And so we have partial psi partial t plus dcj minus alpha kappa times the gradient of psi is equal to 0. And now we're gonna stuff in that kappa is equal to the divergence of the normal vector, which is equal to the divergence of this crazy expression here. And at any rate, what you wind up with, again, if you just sort of leave it in this form, but what you wind up with here is that you have partial, you can actually break this into the DCJ portion and this curvature portion here. And what you'll find is that basically you have the time derivative here. You have basically this portion here that propagates the detonation surface outward. Basically, it propagates the surface outward uniformly in the normal direction at the Chapman-Jouguet detonation velocity. And this here is basically called a sort of Heightens motion, and that basically conforms to Heightens basically Heightens rule, and I'll discuss that next. And this term here, it becomes more apparent if you expand this term out, but basically this here is a curvature term. It's diffusive, and it acts like surface tension in fluid mechanics. And so basically, if you have, say, a sharp corner like this in the detonation structure, I don't know how you could have that, but basically, if you turn this term off and just looked at this term over here, what the basically, if you started with, say, a square detonation wave, what this surface tension like term would do is it would actually start to turn it into a circle, because this curvature term, it would be 0 here initially, 0 here initially, 0 here, but very high on the corner. And then basically what this curvature term is going to do is it's basically going to round off the corners. And a lot of the behavior that you'd see when you evolve the surface, it'll look a little bit like what happens in fluid mechanics if you are doing, say, surface tension induced motion of a droplet. Or something like that, is that if there's a sharp corner that you define from the initial conditions of your simulation, a surface tension will basically quickly round off that corner, and then basically try its best to basically turn the shape into a perfect circle in, say, 2D or a sphere in 3D. Okay, but also in general, this curvature term, it's diffusive. It sort of tends to round off corners and things like that. So it's a really interesting term. And so, and if you sum up both, if you do both of these together, you find that you'll basically get the net motion of the detonation. Okay. And if these two terms here are equal, the detonation does not propagate. Now, from a practical standpoint, numerically, you are at the mercy of numerics as to whether, if these two are mathematically perfectly balanced, as to whether any code that you write will basically balance everything perfectly. And that's not always the case. But yeah. Okay, but in general, you're not interested in really any practical application where the curvature would be so high that you leave dead zones. Now, you may be interested in that from the code to predict those, because you want to design around, you want to avoid those dead zones where you have unburned reactants that don't participate in the detonation. Okay, so are there any questions with that? And so really, what this turns into, if you have this nice simple rule for the detonation velocity as a function of curvature, it basically turns into a sort of a nonlinear heat conduction problem. It's just that it doesn't look like it's a heat conduction like term, but if you were to expand these out using this, you would see that it'd be a really weird nonlinear heat conduction term. Okay, and then in the level set code that I wrote for you guys to use for project 1, this is the equation that actually that code solves. And basically, your project will be to determine alpha, and then to basically use that code to predict the propagation of the detonation over I think it starts from a circle and it has to sneak around some sort of rectangular object like that. Okay, and that's based on an experiment that was performed at Eglin Air Force Base about 10-15 years ago. Okay, so are there any questions on that? So I mentioned Heightens motion, and again, I'm not an artist, so I apologize for that. But basically, what that means, and basically this is sort of Heightens rule. It's the same thing you may have learned about wave motion back in the day in either high school physics or college physics. It's the same thing, and basically what that means is that if we start with a surface, that means what basically Heightens motion means is that every point on the surface propagates normal to itself at the same velocity. Okay, so that's basically what it means. So if I have, say, a jagged surface like this, and every point on the surface propagates normal to itself for a time delta t, that means if I draw the new position of the surface, any point, the distance from basically any point on the new surface to the old surface is the same. And so that means the thickness of this band here, even though again I can't really draw it, will be the same everywhere. Okay, and so that's basically what sort of Heightens motion looks for. And basically, if you have a point and basically that propagates outwards, because every point has to be because basically every new point on the new curve has to be the same distance from the old curve. That means that basically this point here will basically turn into a circular arc at new time. And any cusp here like this, well, again, basically the distance here basically needs to be the same, but this cusp here starts to go away as we start to move basically more and more inwards. And then if we do the same thing again and we basically propagate the surface for a new delta t, again the second surface here has to be the same distance at all points from the first surface. And then basically, again, I can't draw it, but the band here they will all have the same thickness. And basically this process keeps repeating itself, and eventually these sort of circular arcs that are produced by these regions here basically start to overtake everything, and the sort of inward and sort of backwards facing points or cusps actually start to basically start to disappear as the circular arcs basically start to overtake them. And so eventually what would happen is, if this was a full enclosed surface, eventually if you look far enough away, it would start to look like a perfect circle as you got farther and farther away from the surface. Again, this Huygens motion is assuming that all points on the surface are moving locally at the same velocity. And so this, even though it's not really accurate, this Huygens propagation is commonly used in modeling just the bulk effect of an explosive, because you don't always know alpha, you don't always enough about alpha to even predict it, but you always know enough about the explosive to compute DCJ. And so sometimes folks just forget about using Dsd theory, and they just use Huygens propagation of the detonation surface. And so part of your project will be to compare Huygens propagation to the result using Dsd theory, and you can do that. You can do that in the code by just setting alpha equal to 0. Okay, and so again, you'll see Huygens propagation being used when we discuss burning propellants, because again, those also propagate normal to themselves. Okay. And now for this Dsd theory, here are some examples from a paper from a student, a famous student of Scott Stewart's, Tarek Aslam, Bazil and Stewart. Their d kappa relation is here for their explosive. I think they use this curve directly in their level set evolution equation. And so here they just have some examples of it. I know this is hard to see, but here they have a planar detonation, and it's encountering a channel that has a slope like this. And this upper left here, they actually solved the reactive burn equation. So those are the full two-dimensional solving a formalized reaction model, everything. And so you could sort of deem the curves here as being exact. And notice here that as the detonation interacts with the surface, what happens is that the detonation surface, as it propagates, becomes curved, and it becomes inwardly curved with negative curvature. That means the detonation speeds up, and you can tell it's speeding up here. And at the middle, it's still propagating by sort of Heightens rule, because there is no curvature, and you can tell that because the distance between these lines are all the same. But on the top here, where there is some large negative curvature, the points here are actually farther apart than they are down here. And so basically that means there's a substantial curvature effect here. And so this here is the same plot, but it is using Dsd theory. And so Dsd theory basically gets the curves. This here is ignoring, is propagating the surface using Heightens rule. And the thing about Heightens rule is it just predicts a nice flat planar detonation propagating through this channel, which you can see is completely wrong. And the reason that it stays perfectly flat is with Heightens rule is that the rule is a detonation propagates normal to itself. There is no diffusive term or anything like that that allows the detonation to sort of communicate with any sort of wall. And so it just sort of crashes into it, and it doesn't even know that it crashed into it. And now in this plot here, they compare the results of Dsd theory versus the direct numerical simulation here. And so these lines here, the vertical lines are from Heightens rule, and then you can see basically there are two lines for each of these curves, and one is for this, and one is for this this whatchamacallit, for the DNS calculation, and the other B is for the DSD calculation. And so you can see that the error of using Huygens method is pretty high, and using Dsd theory is actually pretty good. And so in this case, the Dsd theory and the DNS are very close, which means that our curvature of the detonation is low enough to where we are in the asymptotic limit, where basically a Dsd theory is designed to live. And I'll just go over this one extra example. Here we have a detonation propagating into a region with a larger area. And so what we see here, again, I'll start here. This here is sort of Huygens propagation. And you can tell that because, again, the distance from any point on the detonation between the different times, they are perfectly the same. Okay, and so basically the distance between here and here is the same as it is between here and here. But if we look at the direct numerical simulation results, are the reactive burn calculations and DSD, we see that there's a substantial influence of curvature. And you can tell that because down here, where there's no curvature, these sort of follow Heightens Rule sort of nicely. But here we have large, but on the top here, we have large positive curvature, which means that the detonation is moving slower in this region here than it is down here. And so basically these points here are basically closer together. If the points are closer together, that means that portion of the detonation surface is propagating more slowly. And so here, again, they compared the influence of the direct numerical simulations to Heightens Rule and to Dsd Theory. And so Heightens Rule, again, are these outer lines here. Those are in massive air. And the direct numerical simulations using a full-fledged reactive burn model, those are the sort of lines in the middle and fairly close to them, except for in the beginning bit where the curvature is very high. And we're starting to get into a regime where DSD is sort of on kind of shaky ground, but it still does probably better than Heightens Rule. Okay, and so this Dsd theory does capture some of the effects of full-fledged reactive burn simulations, and so it's used for a lot of explosive designs for either the military or even for blasting, like rocks and things like that, or for the Department of Energy. And I'll let you use your imagination why they care about this stuff. Okay, so are there any questions on this? Okay, that's it then for today. I'll post the videos fairly soon. I'll post the new homework fairly soon. I was going to do all that stuff yesterday, but I decided it's prudent to go and get a needle stuck in my arm.
Thank you.